Hello everyone. Hmm. I can see that there are only two people watching. With one is me. Now it is actually three. So let's wait for remaining. Hope that my voice is clear. So today is just an introduction session. I just wanted to check how the things are working on. Is the video uh, clarity okay? Is the audio clarity okay? How are the things in general? Is it really practical or something? So I don't know how I'm going to interact with all of you. I think we can do that using some kind of a chat facility here, which is given by YouTube. So uh, let me just check this. Uh, I think in the right side of the YouTube, you will see a live chat window. So you can respond with yes or no if I ask a question like, how about the video quality and audio quality? Are you able to see the chat window here on the right side in that YouTube browser screen? Alright, so Anirudh has confirmed that the audio and video clarities are pretty okay, and so we can go ahead with the class now. So there won't be any need of writing the notes. So I will be speaking continuously for around 1 hour, and whatever notes are required, I will provide you the same within a couple of days, maybe 1 or 2 days. In fact, I am working on the notes. So whatever minute details I am covering in the lecture, the same things will be written on the notes, I guess. So no need to worry about that part. And hopefully after this semiconductors course gets over, you will have a very good clarity on the entire topic, and you will be able to solve almost all the questions which are on the level of JEE mains and board exam. So semiconductors are actually a very important topic. If let's say we compare the two chapters of rotation and semiconductors, from both of these chapters the questions are going to come in equal number in mains exam. But one is very difficult, rotation, so many concepts are there, and we know that so much of practice is required for mastering that topic. But here this is a theoretical chapter with some here and there small concepts and some very simple numericals, and if we understand this chapter quite properly, then we should be able to crack any questions. Okay, so without wasting any time, let's start the semiconductors here. I hope that you all are ready with your NCERT textbook, because we will be referring to some facts which are given in NCERT textbooks, and also some statements which are very important that you need to note down from the NCERT textbook. You can mark on that book itself. So let's start the topic. So once again, so thank you very much for attending these classes, and let's start. So what are semiconductors now? We know that all the materials can be classified into three categories. We know that there are metals, and then there are semiconductors, and then there are insulators. Okay, so these metals are classified according to their electrical conductivity. So if you open page number 468 of your NCERT textbook, you can see the conductivity ranges and resistivity ranges for the metals, semiconductors, and insulators. As we can see from the facts which are given in that page, that the conductivity of the metals is roughly around 10 raised to 2 to 10 raised to 8. So that's a very large conductivity, whereas on the other hand the insulators have the conductivity of around 10 raised to minus 11 to 10 raised to minus 19. That is extremely small, and semiconductors fall somewhere in between with an average conductivity of around 10 raised to minus 6 to 10 raised to 5. One other thing which I forgot to tell you before is that how are we going to discuss some doubts that we are going to have, I mean, during the course of the lectures. So what we can do is that we can discuss those doubts in the WhatsApp group itself via a chat or something, and there you can post the queries. All right. So moving on now. Now, why the semiconductors are very important? That's because we can control their conductivities. Metals are extremely highly conductive, and we can't do anything about it. Whereas insulators, on the other hand, their conductivities can't be changed at all. They are highly insulators and always insulators. Whereas semiconductors are those substances whose conductivity can be changed, increased or decreased according to our will. Doing certain things in the semiconductors, like increasing the temperatures or adding some impurities, may change the conductivity to very drastic levels. Not only that, the conductivities can also be changed in directional manner. For example, we may allow the current to flow in one direction, whereas we may restrict the flow of current in other directions. So these kind of controls that we have in semiconductors makes us able to use them in those circuits in which we want certain things to do when certain things are required. For example, when we are working in a mobile phone, and when we press something like a button, we want a certain thing to happen when a certain kind of input is given. So what kind of output should be generated according to what kind of input? So for that, some kind of a logical flow should be there, and those things can be achieved using the semiconductors. So these semiconductors, as you all know, are made up of fourth group elements like silicon and germanium mostly. So the conductivities of the silicon and the germanium, which is the fourth group elements, they are neither actually metals nor they are actually completely non-metal, so somewhere in between. So let's consider the silicon atom, and let's write its electronic configuration. So its electronic configuration, since it has got 14 electrons, so it will be like 1s2, 2s2, 2p6, 3s2, and 3p2. So that is what is the electronic configuration. And now there is something called Pauli's exclusion principle. This is where the semiconductors theory begins. Pauli's exclusion principle. So what is this Pauli's exclusion principle? Well, there are many statements regarding Pauli's exclusion principle, but one statement of it that we are more concerned about here is that no two electrons in a single system can have exactly identical energy. Okay, I can see some message from Mahesh here. Uh, Shreyas Mahesh, that can we ask doubts in the live chat here? Um, the thing is, okay, fine, but I think you can ask. Yes, that's not a problem. So I will switch back and forth between my notes in the laptop and the YouTube screen. So once in a while, I'll be looking at the doubts here. Yeah. So go ahead with the doubts. Anyway, so coming back to the Pauli's exclusion principle here, no two electrons in a single system can have exactly identical energies. Let's draw the energy levels of these orbitals, different orbitals. We know that we have nucleus, and then we have the closest to them is the s orbitals of the first quantum number, and those are since most closest to the nucleus are having the least energies. In fact, the valence electrons are having the highest energies, and the innermost electrons have got the least energy. So if we draw these energy levels, we have 1s around here. This will be the energy level of the, let's say, 1s electrons, and then we have here the 2s. Now 2s and 2p will have similar energies because of same quantum principal quantum number, and then we have 3s here, and then we have here like 3p. So let me just draw here 2s2, and here we have 2p6, and then we have 3s2 and 3p2. Okay, so in 1s we have got 2 electrons, and in 2s also 2, and then in 2p there are 6, and in 3s there are again 2, and then in 3p orbitals 6 can be accommodated, but then we know that only 2 are there. So out of this 6 energy states available, only 2 are filled, and these 4 are vacant. So we are talking about here a single silicon atom. Now what we have done here is that for these 2 electrons in this 1s, we have given same energy. Whereas if you see this 2p, in this 2p there are 6 electrons, and to all of these 6 electrons we have given exactly same energy. But actually that's not the case. What actually happens is that these 2 electrons in 1s, they have got slightly different energies. For example, here the energy of this electron, if it is somewhere around minus, maybe just for an example, minus 50 point, let's say 24, then this electron will have some energy of somewhat equal to minus 50 point, let's say 25. So there is a slight difference in the energies of the 2 electrons, and here also there will be slight energies in the 6 electrons of this 2p. Just hold on for a minute, I'll be right back. Yeah, sorry for the interruption. So let's proceed once again. So as I was explaining, there are slight energy differences, but these energy differences are so small that if we try to draw these energy lines for all of these 6, they will come so close that these lines will be exactly like coinciding. So that's why we have not drawn 6 different lines here, because all of these 6 different lines corresponding to 6 different energies are so close, because the energies of these 6 2p electrons are very close to each other. Okay, but what happens when, let's say, another silicon atom comes in very close to this silicon atom? So all right, so actually we can go ahead with this one only. So now let's say we have this silicon atom, which we are representing using these orbits. So there are 2 here, and then like that 8 here. Okay, 1 2 3 4 5 6 7 8, and then we have 1 2 3 and 4. Okay, so this is one silicon atom. If now another silicon atom comes close to it, then what will happen? Then interaction between the two silicon atoms will start. When these two silicon atoms were very far away from each other, then they were isolated. They could not interact with each other. They could not apply electrostatic forces of attraction or repulsion or other forces of attraction or repulsion on each other. But now that they are brought close together, they are interacting. So the nucleus of this silicon atom, which is the previous one, will interact with the nucleus of another silicon atom which has come new. Not only that, the second nucleus which we have brought near, that second nucleus will now attract the electrons of this already present silicon atom. And so these energies will change. Obviously the electrostatic potential will be, energy will be changed. Why the electrostatic potential energy will be changed is because now we have got new charges. So if you consider this valence electron here, earlier this valence electron was in the electric field of this nucleus and the remaining electrons. But now this electron here, this one, now this is influenced by the other nucleus and other electrons. And so now since there are different charges here and different charges are there, so we can make many more pairs here. And because of that, we can say that this electron's energy is now changed. Okay, so its kinetic energy will also change because now there are new forces, and new forces will do some new work on it and they may change the kinetic energy. So overall what will happen is that the system's energy will change. When this silicon atom is there, let's say it has got this 1s, and then it has got this 2s and 2p, and then it has 3s and 3p, and this silicon atom also has now 1s, 2s, 2p, 3s and 3p. And let's say this 3p, the two electrons in 3p were having energies, for example let's say minus 14.24, and this electron was also having, let's say, energy minus 14.25, and let's say this silicon atom also had this 3p electrons, and this was also having, previously before they were brought close, this electron was having minus 14.24 and this electron was having, let's say, minus 14.25. So these were the energies when they were isolated from each other very far away, but now we have brought them close. Earlier this electron could have energy of minus 14.24 and this electron could also have energy of minus 14.24. Why was that? Because they were not in a single system, because this was a different system isolated from the other one which was also forming a different system. But now when they have been brought close and the two atoms are interacting with each other, these two electrons, this electron here 1 and this electron here, let's say 2, this 1 electron and 2 electrons are within the same system now, and because of which these two cannot have any more same values of energy. So what will happen is that the energy of this electron will slightly increase or decrease, and energy of this electron will slightly increase or decrease. Maybe this electron's energy will now become minus 14.23 and this electron's energy will become something like minus 14.235 or 245, something like that. Not only that, this electron's energy will also change. Earlier this energy was minus 14.25 and this was also minus 14.25. So this energy will also change now, and this energy will also change now. Now why? Because they are now in the same system, and within the same system no two electrons can have exactly same energy. Okay, we got a doubt here from Avinash, that it is saying that you said for 2s and 2p the energies are similar due to principal quantum. Then shouldn't 3 also have similar energy due to the same principal quantum? Yeah, so 3s and 3p will also have the similar energy, but still they are different from each other as compared to the electrons of the 3p. So if 3p's energies of electrons are similar to each other and 3s electrons energies are similar to each other, but there will be difference between the 3p electrons and 3s electrons. So although they are having similar quantum number, the energy of 3p and 3s will be somewhat similar and somewhat different also. There will be some kind of a gap between 3p and 3s. So moving ahead now, it is more like this for example, hydrogen molecule is formed. You know that when the molecular orbitals are formed, one molecular orbital has got higher energy and one molecular which is called like anti-bonding orbital, and the other orbital which is formed is having lower energy, which is called the bonding orbital. So the energy gets redistributed. One energy may increase, other energy may decrease, and the overall energy remains same. And we know that the lower energy bonding orbitals are filled before the higher energy anti-bonding orbitals. So somewhat similar to this. Okay, what if we have not two silicon atoms but thousands of silicon atoms which are forming, coming together and forming some kind of a crystal lattice? Okay, so if the 3p energy was here and 3s energy was here and 2p energy is here, 2s energy is here, and this is 1s energy. If we bring, let's say, thousands of atoms here of silicon, 1000 atoms, so how many 3p electrons are there? Each silicon atom has got two 3p electrons, so one electron here and another electron here. But now we will have 2000 3p electrons. Previous to bringing them close, each of these 1000 electrons had energy exactly minus 14.24, and the other electron had exactly minus 14.25. But now when we bring those 1000 atoms together, then they form a single system. They start interacting with each other, and since they are in single system and no two electron can have exactly identical energy, so some electrons energy will increase, some electrons energy will decrease. So previously when it was 14.24, it will become 14.25, 14.26, 14.27, and then it will also become 14.23, 14.22, and 14.21 and 14.20, like that. So instead of having one single value of energy here, we will have many values of energy, and this happens when the separation decreases. So as the separation is decreased here, this is the decreasing separation. What happens is, instead of having one single energy, we have a range of energies, and this range of energies are very close to each other. If previously there was minus 14.24, now there will be many electrons having energy slightly greater than 14.24, and there will be many electrons which will have energy slightly less than minus 14.24. So this is called the splitting of energy levels into an energy band. Now why do we call it as some kind of a continuous band? That's because the energies of the electrons are very close to each other. So it's like a continuous variation of energies. Alright. So I guess the audio and video are clear. Am I writing too small, or are you not able to see from that video, or is it fine, the font wise? Can you just give me a feedback on this? The size of the alphabets typed by me. Okay, page moving up a little bit will not be possible, I guess. But what I can do is I can keep something which is, but it will be difficult for me to write it. Okay, so I have kept this free copies. Hopefully, it will help. Okay, so moving on now. As I was explaining, instead of here one single value of energies, there will be lots and lots of energies here. Similarly, this 3s electron. 3s electron will, we know that it will have a smaller energy. So let's say this small energy was somewhere around minus 18.25. So each of these 1000 atoms had got this 3s electron, which had it exactly had this same 18.25 energy, but not anymore, because they are going to form a single system. So these electrons which were having exactly minus 18.25, some will have energy greater, so this electron, and some will have energy less, which is like this. Alright, so here also this a single energy level will actually split into a energy band, and this is actually called the energy band theory. Okay, then what about the 2p, 2s and 1s? The thing is that these inner orbits and inner orbitals are very close to the nucleus, and the interaction first starts only on the valence shell electrons. Okay, Ankur is saying no, no, not like that. So I guess it's quite in range now. I will just move it a little bit here. So all these things I need to keep in mind. In fact, I am also pretty nervous, as this is my first time. So I need to learn all these small things while taking online videos, that the page should always be in the proper orientation or something. Okay, so moving ahead now. Yeah, so coming back to this. So as I was saying, when these atoms they come closer, this interaction between the outer orbits and outer electrons start first, and these inner electrons are still shielded, and so the interaction between them doesn't start that much fast. So what happens is that in case of this 1s, only when the separation decreases to very low value, so that these inner orbitals can also start to interact, and then only they will start to form a single system, and then only the energy levels will start to split into bands at a very small radius. Okay, so coming back to this splitting here, as the separation becomes lower and lower, what happens is that the energy gap keeps increasing, this the energy band here, so much so that when the separation is decreased to some value like this, then the energies merge, which means that the energies of this 2p, the energies of this 3p and energies of this 3s, they are like overlapping with each other, and this we call as the merging of the energy bands. And now we can't distinguish between which one is like 3p and which one is like 3s, because now that they are merged together. Okay, as we keep decreasing the distance, what happens is that these energy bands which have actually merged, they start to split once again. like this. So now there will be energy bands here, and there will be energy band here also, but in between there are no bands here. I mean, there are no possible energies. Now why exactly does this splitting starts, that is actually beyond the scope of our understanding. In fact, I was going through a course by Professor Kalmakar in IT Madras, and he was taking a course for the first year students, basic course in electronics, and he also, while highlighting this point that the bands again split, he said that we can't understand it right now. So for that, some kind of a quantum mechanical phenomena happens, and beyond the syllabus. So just leave it and just memorize it as a fact that once these energy bands from the 3p and 3s, when they expand and then they merge, then as we keep decreasing the radius, as we keep decreasing the separation between the two atoms, then these bands split again. Now, how many energy states are required and how many energy states are available? For that, we need to understand certain things. Let's say we had got 1000 atoms, and each of the 1000 atoms had got this 1000 3s electron. So how many energy levels are required for this 1000 atoms 3s electrons? Since we know that there are two 3s electrons, we require 2000 levels. And here again there are two electrons in the 3p, but then there are other vacancies also there, and the electron can actually come here because this is a vacant orbital, and a vacant orbital actually signifies a vacant energy level also. So let's say if we have, instead of 1000, let's say we have n atoms. So if we have n atoms, then we have got 2n 3s electrons, and we have got here 6n energy levels 6n energy levels in 3p. But out of those 6n energy levels, only 2p will be filled, 2n will be filled, and remaining 4n will be vacant in this case. So here how many energy levels will be there? 6n energy levels. And here how many energy levels will be there? 2n energy levels. And in all of these 2n energy levels, 2n electrons will be there. And here in all of these 6n energy levels, only 2n electrons are there filled up, and remaining 4n energy levels are vacant. Whereas here, all in this case of 3s, all these 2n energy levels are filled with those 2n electrons of that n atoms of silicon. So, but what about here? This 6n energy levels of 3p and 2n energy levels of 3s, with a total of 8n energy levels, they actually merge, and when they merge, they form a continuous total 8n energy levels. So one energy level here, one here, one here, one here, like that there will be 8n energy levels in total. But when these bands split again, these energy levels are split equally into upper energy level and lower energy level. So here there will be 4n energy levels, and here there will be like 4n energy levels. Okay. These 4n lower energy state levels are there, and this 4n upper energy level states are there. Now, as we keep decreasing the radius, as we keep decreasing the separation between the atoms, finally the graph may go something like this also. Actually, it is given in your NCERT textbooks. If you open page number 470, you can see the diagram there. And it's not that we can decrease the distance between the two atoms to very zero. There is something called lattice constant. And what is lattice constant? lattice constant is the average separation between the two atoms in a crystal lattice. So if we have, let's say, some kind of a molten silicon, and when it solidifies and it forms a solid crystal, in that solid crystal, silicon, which follows FCC, face centered cubic, the average separation between two atoms roughly is around this level. And in this separation, this is the actual spacing between atoms. This is the actual spacing. So the atom doesn't crystallize somewhere here or here or here. The atom actually crystallizes with the average separation here, like this. And so there are four energy states available here and four energy state levels available here. If we take very very low temperature, in which the crystal lattice has got extremely low energies. See, low temperature means the low energy of electrons also. If we apply that same Boltzmann constant rule kind of thing in case of electrons also, so each electron's kinetic energy comes out to be nearly equal to 3 by 2 kT kind of thing. So at very very low temperature, the kinetic energy of the electrons is very very low, and in fact the total energy is also very very low. And so in lower temperatures, the electrons are there in this lower energy states. In fact, in perfectly 0 Kelvin, in a perfectly 0 Kelvin, in perfectly 0 Kelvin, all 4n lower energy states are filled, and all upper 4n energy states are empty. This is the condition at perfectly 0 Kelvin. Okay. See how many electrons are there in the valence shell. There are 4 electrons for one atom, and there are n atoms, which means 4n electrons. These 4n electrons have got these 8n options. Instead of choosing the upper 4n options, these 4n electrons go to the lower energy 4n atoms, 4n energy levels. These energy levels and this band of energy levels is called the valence band, VALENCE, valence band, and these upper energy levels are called the conduction band. And remember that we are talking about valence shell electrons only. Valence shell means principal quantum number 3, and we are discussing about those electrons, and those electrons at 0 Kelvin all occupy this 4n. But as the temperature is increased, what happens is that these electrons are able to jump from this lower energy valence band to higher energy conduction band, and to jump to from the valence band to the conduction band, they have to overcome this energy barrier. Now this energy barrier is called the forbidden energy gap. Okay, moving on now. So once we again plot the energy levels here, but not for a silicon atom, but for a entire crystal structure. So let me just adjust this. Yeah, I think it is proper now. So this is like a 1s energy level, and then here we have a 2s energy level, then 3s, sorry, this is 1s, this is 2s, and let's say this is 2p. And instead of exactly 1 3s and 3p, we have got this valence band, and we have got this conduction band, and these are the energy levels. So we will call this as valence VLENC, and this is the conduction band. And the difference between these two, the energy level of the lower energy level of conduction band and higher energy limit of the valence band, the energy gap between them is called the forbidden energy gap. Forbidden energy gap. As the temperature of the silicon keeps increasing, more and more electrons able to get energies, and they are able to jump from valence band to the conduction band. So two things basically will done, that at 0 Kelvin all the valence band are filled and all conduction band are empty. And second thing is that as the energy keeps increasing because of increase in temperature, then many electrons are able to shift from valence band to the conduction band. Now what is the meaning of shifting to conduction band or higher energy levels? See here. Let's draw two atoms of silicon. Let's say this is a nucleus, this is and then there are these three here, and then we have another nucleus here of another silicon atom, like this. Yeah, so this is the outermost electrons. When the interaction between them, between the first atom and the second atom starts, this valence shell electron may be equally pulled by this nucleus as well as by this nucleus, provided the distance between the two atoms comes out to be very close. And so we say that this electron is not necessarily bound to this atom only, but it is equally bound to the second atom or second nucleus. And so we can say that instead of revolving like this in the orbit of the first nucleus only, rather we will say that now it is combinedly bound to these two atoms, because these two atoms have become very close to each other, and because of which there is an equal attraction from both the nucleus and it's part of both the atoms now. And so this electron can go here also like this, and in fact it can move like this, so its motion will be something like this. And so these electron will be able to move not only from within the circle, but it will be able to go to the other atom. And what if we bring 3? And so if we bring 3, then it can go even to the third atom like this. And what if we bring 1000? Then it can go everywhere near the 1000 atom. And we say that this electron has now become free. So what is a free electron? Free electron is an electron which is not exactly bound to a single atom, and actually it is free to move within the entire volume of the material. And so this free electron can conduct electricity because it is free now. Now, in which electrons the attraction from the other nucleus will start first? Obviously on the outer one. Then what we can say about the inner one? See, these inner electrons are still more attracted by its own nucleus as compared to the other nucleus because of the large distance, isn't it? And so this electron of the inner shell won't be able to go to the other parts of the crystal lattice because it can't leave its nucleus, because it is tightly bound to this nucleus because of higher attraction. So this electron inner cannot conduct electricity. It's electricity outside. So we can say that the higher energy level electrons which are there on the outermost kind of thing, they are able to conduct electricity. What is found is that these electrons in this higher energy levels of this conduction band, these electrons here, they are able to conduct electricity, and these are not able to conduct electricity. So these electrons in the valence band are not able to shift to other nucleus. They are bound to the same nucleus and they are not able to conduct electricity, can't go anywhere, whereas this electrons in the conduction band, that's why the name comes actually the conduction band, that the higher energy electrons are able to go and roam around the entire crystal lattice, thereby conducting electricity. Okay, moving on now. as we keep increasing the temperature, more and more electrons will be able to go from valence band to conduction band. And since more electrons are available to conduct electricity, so definitely the conductivity of the material will increase. So if the conductivity increase, then it will conduct more electricity. So that's why we say that the for the semiconductors, as the temperature keeps increasing, the electricity conduction or the conductivity is more because of more availability of free electrons that can conduct electricity. Now there is something called Ni, which is called intrinsic carrier concentration. Intrinsic carrier concentration. For understanding that, we have to understand first there is something called atomic concentration. Atomic concentration. So what is this atomic concentration? It is actually the number of atoms in 1 centimeter cube of the material. So here actually I already wrote these things, so I hope it is focusing properly. Yeah, so let's say if the density of silicon is rho gram per centimeter cube and its molar mass is obviously 28, that means that we know that molar mass 28 means 28 gram means 1 mole, which means this many atoms. So 1 gram is this many atoms here. If we, so 1 centimeter cube means rho grams, and 1 gram means this many atoms. So rho gram means this many atoms. Now density for the silicon is somewhere around 2.23 gram per centimeter cube. So we say that in 1 centimeter cube of silicon, if we substitute the value of rho here, then we'll get this. So this is the number of atoms in 1 centimeter cube of silicon, which is roughly around 5.0 into 10 raised to 22 atoms per centimeter cube. This is what is called the atomic concentration. Then what is intrinsic carrier concentration? This intrinsic carrier concentration represented by Ni, this is the number of free electrons per centimeter cube that are available to conduct electricity at a given temperature. Obviously, as we know that as the temperature increases, the number of free electrons available will be more and more, because more electrons will be able to jump from conduction valence band to the conduction band. So this is very important, the intrinsic carrier concentration. What is found is that practically the intrinsic carrier concentration of silicon at room temperatures is somewhere around 10 raised to 16 electrons per centimeter cube. Per centimeter cube, yeah, I guess it is. Wait. Anyway, I will just check this number once. Now we have to understand what is something called holes. To understand what are holes, we have to understand what is the silicon's crystal structure. Silicon's crystal structure is a FCC. So we all know what is FCC. So there will be 8 here, and then there will be 4 here, and then apart from these 4, there are 4 more. So if we go A by 4 here, if A is a lattice constant, the length of the cube, then A by 4 here if we go, then if we go A by 4 here, and then if we go A by 4 up, here is another atom. So it's like a diamond kind of structure it follows. Okay. Now each of this silicon atom is bound to 4 of its closest neighbors. Each of the silicon, here also it will be bound to this one, and then this one, and then somewhere like this, and then somewhere like this here. Each of the silicon atom is bound to the 4 of its neighbors. And although this is like a 3D kind of model, what we do is, for simplicity, we write it in terms of a 2-dimensional silicon mesh. So how we draw it is, we draw a lot of silicons in something called a mesh-like structure. Silicon, and the silicon atom shares these electrons with its 4 neighbors. So this shared pair, this shared pair, this shared. So there are these four covalent bonds which the silicon atom forms here. Now what happens when an electron jumps from a valence band to a conduction band? Then for example this electron here, this one. If this electron jumps from valence band to conduction band, we know that it is now no more attached to this silicon atom and it can go all the way anywhere around the crystal. So we say that this electron is gone now and it is somewhere here, and this electron can now go anywhere. So there is some kind of a hollow or vacancy created, and this vacancy which is created because the electron is lost from here, this is called a hole. And let's say there is one more electron which is this electron. This electron has also left its place and now it has gone somewhere else and it is roaming all around the crystal lattice, and again there is a hole created. Now what if we apply here an electric field? For example, if we are applying electric field here like this is how the electric field applied in the crystal lattice. Then obviously these were the free electrons. In which direction will they get a force? They will get a force opposite to the electric field, and so they will start moving here. So this is the direction in which these free electrons will start to move, and since the electrons are starting to move, so they are going to create current. So this electric field E here will create a current like this. So the current is carried by these free electrons. But what about the vacancies here? We know that there is a vacancy here and there is a vacancy here. Now we know that there is an electric field which is applied like this in this direction, electric field, and so there is a force like this. Now what may happen is that because of this force like this electron can jump here into this vacancy, and if this electron comes here and falls into this vacancy, and then there is a vacancy which is created here, and if there is a vacancy here created, and because of this force here, what may happen is this electron here can go into this vacancy because of a force here, or maybe this electron can go, and because of this backward force this electron may go and jump into this vacancy. If this electron goes in here, what will happen is that a vacancy will be created here. So initially the vacancy was here, now that vacancy is transferred here, and so we can say that this electron which was here effectively has gone here. Then only the vacancy will be shifted in this place. So let's say this place was A where the vacancy was there initially, and now the vacancy is here at B. So effectively the electron has been transferred from point B to point A. And so not only these free electrons can move opposite to the electric field to create current, electric current, these electrons within this valence band and these electrons within this silicon lattice, and these electrons which are bound here to the silicon atom, they can also move to the next atoms where there is vacancy, and thus effectively these electrons are actually moving opposite to the electric field, thereby constituting a current. So what we can do is instead of saying that the negative charge has moved from this vacancy this place to this vacancy, we can say that instead of negative charge moving in left direction, we can say that the positive charge has moved here. So we say that the vacancy has been transferred from here to here, and we say that this vacancy is having a positive charge, and this vacancy having a positive charge is called a hole. So in the semiconductors, the current is possessed, or the current is carried or caused by the movement of both the electrons, free electrons in the conduction band. They are moving anywhere throughout the lattice and thereby constituting the current, and this is in the conduction band, happening in conduction band, and this current is happening in the valence band here. So the total current at any given instant of time is written as the whole current plus the electrons current. So I don't know how am I going, because this is also my first time. So I thought of taking this kind of introduction about holes and electrons today. So I guess we'll stop here. So actually I thought of covering much more, but instead I explained very small things. I mean, couldn't proceed much. So hopefully in the next time we will do a bit more, we'll go a bit fast. So if you have any questions regarding this, so we will be discussing in the WhatsApp. So I will stop the live chat right now, and you can give me the feedback actually, what are the things we can change, or how to make it better, because this was the first time doing an online thing, so not very professional or very fluent in this. Okay, so next class we'll cover a lot of topics. So I'm stopping the live streaming here.